Oh, okay, okay. I think it's good.
That's about it. I mean, I need to clean my room anyway, but.
I learned how to not show my face on the thing, and then I should have done it on Halloween.
I'll come out and like hang out probably with my husband. I'll look up first and
Okay.
literally, I'm gonna wear my.
All right, so how did you do on this?
Santa Claus pajamas.
I told you we would go over this. How many did you get? I should have made this a clicker question. A, 2, B, 3. Could have gone all the way to 10 probably. Okay, so how many did you get? Hmm? 0? So do we not look at it?
There's 2 chiral centers, right?
Okay, where are the chiral centers?
In the cyclopentane with the methyl, and then the other. So if it's 2 to the N, there should be.
There should be 4.
Should.
But guess what? There's more than 4. Why? What can you tell me about this? It's fancy. It's a double bond. And how can it be arranged? It can be cis or trans. So how many is there going to be? 6. Because you could go RR cis, RR trans, etc. Okay, so you got to remember that double bonds can factor in because they make diastereomers. Okay, that's what the whole point of that was, to help you realize that. Remember that. Okay, so we're going to start chapter 6. Chapter 6 is about alkyl halides and nucleophilic substitution reactions. Don't worry if you don't know what that means. You probably know what an alkyl halide is, right? What's an alkyl halide?
Yep.
It's a what? Let me make this skinnier. Okay, you have some alkyl group and you got a halogen on it. And what are our 4 halogens? Fluorine, chlorine, bromine, and iodine, right? Okay, okay. So that's what we're going to talk about, is those compounds. Okay, organic halides, there are several types of them. Okay, the main type is an alkyl halide, where you have a halogen bonded to an sp3 hybridized carbon. So a good example of that will be okay, that's just a regular alkyl halide. So you could have a methyl, an ethyl, a propyl, a butyl, etc. You can have chains on them too and branches. Okay, those are alkyl halides. Notice that this carbon right here is sp3 hybridized. Okay, a vinyl halide is when you have a halogen bonded to an sp2 hybridized carbon in a double bond. So for example, this would be one of the simplest ones, because you have to have 2 carbons to have a double bond, right? That one is vinyl halide, or vinyl chloride. It's used to make polyvinyl chloride. Have you heard of that? Have you heard of PVC pipe? Okay, that white pipe stuff? Yeah, that's what it's made out of, that. Okay, an aryl halide is when the halogen is bonded to an sp2 hybridized carbon of a benzene ring. So remember that a benzene ring is a 6-membered ring and has alternating double single bonds. Doesn't matter if you put your alternating on the other ones, it's okay. Okay, so you would have a halogen. Let's see, I use bromine and chlorine. Let's put iodine there. Iodobenzene. Okay, that's an aryl halide. We're not done though. There's two more. They're on the next slide. Okay, you ready?
No.
No?
Okay.
You ready? You sure, Caitlin? All right, so an allylic halide is where you're one carbon away from a double bond. All right, so look at this. Here, I use fluorine because we hadn't used that one yet. Now you've seen all four halogens. No astatine. We're not going there. Okay, so there's an allylic halide. Notice it's on a carbon next to a double bond. Okay, and a benzylic halide is one carbon away from a benzene ring. Okay, notice it's on a carbon next to a benzene ring, which are going to be important. You'll see why coming up. Okay, another way that you'll see benzene written is with a pH or a C6H5. The pH actually stands for phenyl, which is another term for a benzene ring. It's a phenyl ring. Okay, so I will redraw the one that I have over there using the shorthand. So that pH means that benzene ring. Okay, that's what it stands for. Another way that you will probably see is C6H5. Notice that there's 6 carbons here and how many hydrogens? 1, 2, 3, 4, 5. There's no hydrogen on that carbon right here, correct? Right? Okay, so then we would write CH2Cl. Okay, so that's that same thing written 3 different ways. It's just 3 different ways to designate it. Okay. Okay, so if I draw this one, I want you to tell me what kind of halide is that? Is it an alkyl halide, a vinyl halide, an allylic halide, an aryl halide, or a benzylic halide? What? Yeah, what kind is it? It's alkyl. Okay, notice it is not vinylic, okay, and it is not allylic because it's too far away from the double bond. So this would be an alkyl halide. Okay, if I put a halogen up here, okay, what kind is that one? Vinylic. Okay, you got it. If I put a halogen here, what's that one? Allylic. Okay, and no, you probably wouldn't have all 3 of these in one. It caused a lot of issues, but okay. Can you read my writing? Okay. Here are some other examples of some different halides. The top one are alkyl halides. You'll notice that chloroform is up here. Have you used chloroform in the lab or no? I know you probably used this one, methylene chloride. I shouldn't have written it there because it looks like it's under vinyl and it might confuse you in your future life. Okay, so quit. Okay, so methylene chloride is another one. Chloroform is also a solvent. Okay, notice this one, CHClF2. Okay, that one is Freon 22. It's used as a refrigerant. So a lot of alkyl halides get used as things like that. Here is one that's cleaning fluid used in dry cleaners. And halothane is a non-flammable anesthetic. Okay, so they would put that over the patient and they would breathe that in. Okay, it's an early anesthetic. Okay, this is vinyl chloride, the one I already showed you. And this is tetrafluoroethylene, which is used to make Teflon. Okay, a lot of the vinyl halides get used to make polymers, which you didn't lab, right? Okay, aryl halides are, where do I have that down there? Okay, aryl halides are, this is paradichlorobenzene, which is mothballs. So it has that distinctive odor, keeps the moths away. And this is an example of one that is a hormone. Okay, notice all the iodines on this compound. This is real important for regulating your thyroid. Okay, it's called thyroxine, and you have to get iodine in your diet in order to make that. Okay, your body makes that. You don't eat thyroxine. I don't think you can. But your body makes it, and in order to make it, you have to have enough iodine. Does anybody know where we get most of our iodine from? Salt. They added it to salt in order to help people get enough iodine in their diet.
Where else would you get it naturally?
Yeah, it's in a lot of fish and all kinds of things. But yeah, we would get it naturally, but we were having issues apparently, and so they did that years ago. If you have an issue with iodine, you can buy non-iodized salt. Okay, so if you go, when you go buy the little cardboard container of the little Morton salt, when it rains it pours. I always thought that was cute. All right, when you get that, you'll look at it and see. It'll tell you if it's iodized or non-iodized. Buy the iodized unless you have a reason to know. Okay, we buy the non-iodized and actually use it to make your saturated salt solutions for washing in the Zephyr. Your stuff that like just fine. It's fine salt. Nothing wrong with it. And it's cheaper. You put a little chemical name on it, sodium chloride, cost skyrockets. Just like medicines, right? All right, here we go. Identify the vinyl chloride. So which one up there is a vinyl chloride? All right, I counted at one point. Now I can't remember. Was it 23? If I counted, it was 22 plus Jeremy was 23. Good memory. He ran out, didn't they? We're sitting here waiting. Okay. Yep, it's B. What is A? What kind? The chlorine is on a carbon next to the double bond. So this one is allylic. I can spell today, barely, allylic. Okay? What is C? Let's do them all. What's C? So what is that called? What kind? Nope.
Aerial.
It's aryl because it's on the benzene ring. If there was a carbon in between, it would be benzoic. Okay? What is D? And what is E? What kind of halogen? Halide. It's okay to have two in a row. Okay? Just different groups. Okay? All right. Remember that fluorine is the most electronegative element. So the electronegativities of the halogens decrease as you go down. They increase to the fluorine, okay? The bond lengths increase as the size of the halogen increases. So a CI bond is longer than a CF bond. Does that make sense? Okay. And here's your dipole moments. 1.56, 1.51, 1.48, and 1.29. Anybody notice that? Isn't that interesting? Okay. Chlorine being bigger actually gives you a bigger dipole moment than fluorine, even though fluorine wins for electronegativity. The molecular dipoles depend on the geometry of the molecule. Okay. And that, right? Because you have to look at the picture. All right, so here are the boiling points. Ethyl fluoride's boiling point is minus 38. So at room temperature, it's a gas, right? All right, ethyl chloride boils at 12. So at room temperature, it's a gas. Okay, ethyl bromide boils at 38. So at room temperature, it's a liquid. Okay, I'm just checking on you. Ethyl iodide boils at 72. So it is also a liquid. Okay. Okie dokie. That's kind of showing you how the halogens get larger. Okay. That picture. Okay, so there's a couple ways to prepare alkyl halides. There's actually more than this, but we're just going to talk about these at the moment. We already talked about the first one, free radical halogenation. So what does that mean? You take a what? An alkane, and you add what? Here's a hint.
Sorry, we're copying down.
Oh.
Questions, well, there's big words.
We're going to talk about all those big words. You just write down the first one, you know, one at a time. Okay, so what do we add to do free radical halogenation? A what? A halogen. Okay, so do you remember what ones worked? We can't use all four. Chlorine and bromine. Okay, which one was more selective? Bromine. Okay, all right. So you will have X2. Okay, is that all you need? What gets this part started? Usually you'll see H new. Okay, and what do you make? What happens in the reaction? You substitute what for what? A halogen for a hydrogen. Okay, and of course there's a lot to which one and all that. I just made it super generic. Okay. Allylic bromination is where you make an allylic free radical intermediate that is stabilized by resonance. Okay, so here is, we're going to go through it. So an allylic compound. Okay, we want to make that compound. So we would start with, all right, let me go through the slide. I need a slide to write on. So concentration of bromine must be kept low or other reactions can occur. So you can't just take one equivalent of your allylic compound and throw in one equivalent of bromine and go, pow, it's going to work. It doesn't work that way, okay? The concentration of bromine must be kept low. You have to allow the free radicals to form. The side reactions, the other reactions, we'll learn about them in another chapter. Okay, N-Bromosuccinimide is a special compound that gets used to make allylic and benzylic bromides. Okay, this is what it is. This is it. You can learn it as NBS. Okay, do you see where the N comes from? N-Bromo. Get that? Okay, this little piece of the molecule here is called succinimide. It's okay, you probably never heard of it. It's all right. That's what it is. It's just that little 5-membered ring. Okay, so what happens is in the reaction mixture, this ends up making your succinimide and a little bit of bromine. That little bit of bromine goes and does what we did in chapter 4. Wasn't that chapter 4? Yeah, all those that free radical thing. Okay, so we're going to do it again. Okay, so here is 2,3-dimethyl but2-ene. So you don't know anything about that nomenclature, so I'm going to draw for you. Okay, so we've got 1, 2, 3, 4, and then we have methyls here and here. Okay, so it's going to look like this. And we're going to use NBS, and you still need heat and light. So we're doing a free radical reaction, okay? But we get 2 products. The 2 products that we get, one is going to be and does it matter which methyl I pick to make this? Every one of them would be the same, right? All 4 of those methyls are equivalent. Okay, the thing is, that's not the only product. The other product that you get looks like this. Whoops, I lost my methyl. You get both of those.
So you get that one plus that one.
Right.
2 different.
Yeah. See how where the bromine is over here? It's on the end. It's on one of the CH3s, okay? Here, the bromine is in the middle, kind of, and the double bond has moved. The reason that happens is because of the intermediate, because it's allylic. So we're going to do it. I'm going to write it all out, and you'll see how you get both of them.
So is it either or you get both?
You get both. It's not either or. You get both. And so at the end, you would have to separate them. Now, those 2 compounds are isomers, but they're just structural isomers. You should be able to separate them by a boiling point or something, because they should have different physical properties, okay, which kind of helps life out. Okay, so I don't know how many blank pages I put. All right, so I'm going to put my little compound. I'm going to write it up here so you know where we're going. Okay. And so here were our 2 products. Plus oops, all these methyls. Okay, so that's not a methyl there. It's just a scribble. It's called a scribble. It's a technical term for it. Okay, so do you remember? Now, first of all, how are you going to know the reaction is free radical? Because that's all we've done so far, Dr. Glassman. Well, we're about to change that. So the way that you're going to know is you look for this. This is like a big clue. If there's H nu, it's free radical. Okay? All right, so what were the steps in our free radical chain reaction? What was step 1? Initiation. Okay. We're going to take our BR, and what are we going to do? This will be good review for the test since we're doing a mechanism very similar to that. Okay, so what do we do? Right, the little fountainy thing. One goes there, one goes there. Okay, remember that when you do free radical mechanisms, you always use half arrows because it's always single electron transfers, and 2 electrons make a bond. 2 electrons make a bond, don't forget that. Okay, so now what did I make? I made a bromine free radical, and I made another bromine free radical. Could you write 2 in front of it? Yeah, you could. I just didn't. All right, so now we got our free radical formed. We're going to start the process. Okay, so what is that called? Propagation. All right, so I'm going to take my bromine free radical, and what do you think it's going to react with? Just like we did before. It's going to react with the organic molecule, and it's going to remove a hydrogen. That's called hydrogen abstraction. All right, so we got, let's see, I'll tell you what. Since it doesn't matter which one I use, I will use this one because it's closer to the bromine. Absolutely no other reason than that. Okay, now remember that it takes 2 electrons to make a bond. So this electron is going to combine with one of the electrons from the CH bond to make a bond. And what happens over here? Where does this electron go? Goes to that carbon, right? Okay. So, try to make that little. So do you see what we made? HBr, okay? HBr reacts with the NBS to make a little more Br2. Okay? Just a little bit at a time. We want to keep that concentration low. All right, so here is my intermediate organic allylic free radical. Okay.
Why is the BRH above that?
Because I was running out of room.
Oh, okay.
For absolutely no other reason than
Okay.
that. Because this thing doesn't let me ride over here, which is where I wanted to ride it. Okay? Because I wanted to put the next step down here. Okay, so now what is our little free radical going to do? What did we do last time? We're going to react with what? Wee-hee. We're going to react with Br2. Oops, lost my thread. Okay. No, we're still propagation. Remember that you only form a real small percentage of free radicals at any given time. And those free radicals are highly reactive. They get used up fast. Okay? So as soon as that's formed, it's going to react. And what is it going to find? The chances are that it's going to find more Br2. Every Br2 in the little reaction mixture is not going, whoo, make free radicals all at the same time. Okay, only a little percent of them are doing that. Okay, that's the key. All right, so now let's this And one of these will make a bond, right? And then the other electron goes to the bromine. So notice what we made. We made another Br free radical. Okay, and we made our product. We'll get to the other product. Okay, so this bromine right here, this is why it's propagation. It can go up and do it again. Okay, this little cycle continues over and over and over and over. Okay, now how do we get the other product? Well, let's look. That's a star that's having a hard time. Okay. Let's look at that intermediate. So we had CH2, here's our free radical, right? Okay, what stabilizes free radicals? What are the things that stabilize free radicals? Induction. And what is that? Through the bonds. Good, good. Okay, so we got this alkyl group here stabilizing. Okay, what kind of free radical is that one, by the way? It's not just allylic, it is primary. Okay, remember, primary, secondary, tertiary. Okay, all right, what else helps stabilize them?
What's through the air? It's like
Hyperconjugation. Hyperconjugation, and that is also from your alkyl group. But there is a third way to stabilize free radicals. And this is the best stabilization of all. Okay, so we're going to draw a resonance form for this structure. You get it because it's allylic. And what is next to the carbon with the free radical? What is that? A double bond. All right, so what we're going to do, this electron and one of these are going to make a double bond. And what happened to the other electron here? Well, it didn't really jump. It just ends up on that carbon. You feel like it's jumping?
I feel like it's jumping.
Oh, that's sore. Okay. Okay, so now what do we get? Now, what are the rules for drawing resonance forms? Draw what didn't change. Then worry about what changed. Okay, so we have this and this and this. None of this did anything, right? Because it should be all hooked together the same way. We don't move atoms in resonance form. Okay, so since I use black, I'll use black. So between the CH2 and this C, what do I have now? Double bond. And what can you tell me about this carbon over here? Yes. See that? Do you see that that free radical is different than this one? That's how you get another product. So you're going to have I guess I switched to black for the second product. Okay, that is going to react with what? This. Okay, so this electron and one from this bond make a new bond. And what happens to the other electron in here? It goes to the bromine. Okay. We're just going to go down because I wrote big. All right, so what are we going to get? We're going to get that, right?
Yep.
That's our new bond. I meant to make the new bond red, but I didn't. Okay, and then we also got a bromine free radical, which can go abstract another hydrogen and do it again.
So that's the part of propagation.
This is how you get the two different products. Okay, now up here, what kind of free radical is that one? It's allylic, but what else is it? Tertiary. So we have tertiary allylic and primary allylic. Boy, that A is sad. Okay, which one do you think is more stable? Ooh, so which product do you think is probably major? This one is probably major. Okay. See how we decided that? Sometimes it might be the same. Sometimes the two are going to be almost identical. So you get the same thing. Okay. So you see how we got that? Now, if you were to write out all the termination steps, you would have to take all of the free radical intermediates and do all the possibilities. So I'm not going to do them. It's kind of overwhelming, isn't it? But somebody's done it and somebody's found them all. They're all there. So like this one could react with itself. This one could react with that one. That, oh my gosh. Okay. It goes on and on. So just worry about initiation and propagation. Okay. Any questions right now? You see how it's really the same thing as what we did before in chapter 4. The only difference is we have resonance. So that gives us another product. Okay, so you got to remember to look for resonance. Look for resonance. Okay. All right, so here's a compound plus NBS. Okay. What are the products? Oh my gosh. Sometimes when you write the bromine, sometimes they don't put it in parentheses and sometimes they do. Do you notice that? Because bromine can only make one bond like a hydrogen. But if it's written in a line like that, it's usually written after the carbon it's attached to unless it's on the end. You could have also written this one this way. Just because we haven't messed with this very much. That's the same thing. Everybody follow? Okay. That this bromine is attached to that carbon. The way that structure is drawn.
Is there not? Is there no delta nu? I just want to be sure.
Oh, yeah, it doesn't matter. NBS only does free radical and sometimes they don't write it. I tend to write it. Yeah, good question. So you might not see it written in the book, the H nu, but I tend to write it. Sometimes just warming it up a little is enough too to get it going. Because that NBR bond just wants to break. Yeah, I probably stole this question from somebody. I don't always like them. I figure if the quilting doesn't pan out, I'll try to write stuff for like clicker questions. Or maybe I'll write for sapling and write questions. I'm really helping the quilting. That's what I really want to do.
Yeah, now I can. Usually I can't.
What?
Usually I can't see, but I just go with the flow.
Oh, okay. All right, we're going to 23. Okay, are we there? If you're my number 23, make a pick. All right, here we go. I'm going to hit it. I guess it's better than nothing. Okay. All right, so what is NBS specific for? What kind of hydrogens? Allylic. Okay, so where are the allylic hydrogens? They're on the allylic carbon. Which one? Where are they? Here's our double bond. One carbon away is allylic. So there are these two. Okay, so you would replace one of those with a bromine. You have to know what NBS means. Okay. All right, so that is one product. Is that going to be the only product? Because what are you going to form as an intermediate? This allylic free radical. Okay, so what do we got to do? Draw the resonance form to decide if there's another product. Okay, there's a bond in there. Okay, so what does the resonance form look like? We're going to have CH3, CH. So I'm going to draw what didn't change. You're changing your answer? Don't change it yet. All right, so now between these two carbons, we now have a double bond, right? Everybody see that? Okay, and the CH2 on the end gets your free radical. Okay, so from the first free radical, our product will be CH3, CH with a Br, CH double bond, CH2. Which one is that? B, okay. Okay, from the second free radical, our product is going to be CH3, CH, double bond CH, CH2, Br. Which one is that one? Which one? D. Okay, so what is the answer? E as in everyone got it right, right? Okay, so how do you figure it out? Number one, draw the allylic free radical that you get from the original hydrogen abstraction. Draw the resonance form. Look at the two. Get your products from those.
So if this was just regular bromation, not would A and C be what would form?
No.
So why is it?
No. NBS is only used because it keeps the bromine in a low concentration. If you added a whole equivalent of bromine, it would add to the double bond and do a whole nother thing. The only way you can get the allylic bromination to occur, the free radical reaction, is to keep the concentration low. That's how come we use NBS. Okay, otherwise, there's a whole nother reaction we haven't talked about for these. Okay, we'd be doing that in a week or two. Oh my gosh. All right, y'all have a good weekend. I will see you on Monday. We will do a review next week too, y'all. Have
would think. Are you taking summers?
Why didn't you tell us?
I didn't realize it till right as you were hitting that. But I believe I got it right. I said E, but I don't think it came through. So